Hello and welcome to this video. In this video we're going to be looking at the forces in a magnetic field acting on a free charge. So we looked at forces acting on a current carrying wire, and we said that the force that acts on the wire, F, is equal to BIL, where B is the magnetic flux density, I is the current, and L is the length of the wire that is submerged into the magnetic field. Then we said that we can have these kind of forces, but we said that they're vectors, and so is the magnetic flux density and the current, because they have to flow in a certain direction, which then makes us, then gives us the requirement of having to introduce Fleming's left-hand rule, which was the kind of FBI gun that we had on the left hand, just using the thumb, your first finger, and your index finger. And you can go back to that video, just make sure you're comfortable with that. Because we're going to need it again in this video. Now, what we're going to say is that a current carrying wire contains moving charges, right? If there's a current flowing, it means there's electrons that are flowing through that wire. And that's actually what causes the force to act. The thing, if we were to get rid of the wire and just have a free electron to travel wherever it wants. So let's say this is my electron here, and it's going to just travel in this direction with some velocity, let's call it v. And there has to be some force acting on this if it enters a magnetic field. Now, the thing that we have to make sure that we're aware of is the direction of current. Okay, now the direction of current, as we mentioned in the electricity section, is actually the current flows from positive to negative. Okay, now that's not the direction that electrons flow in. So the direction of current, what we call conventional current, is the opposite direction, to the motion of electrons. And what we can say from this is it basically follows the positive charges. Okay, so if we had a positive charge like a proton and we were to put it in here, we could use our Fleming's left-hand rule and have the current in the same direction as it's flowing. The thing here is if the electrons are flowing in this direction, it actually means the current is flowing in the opposite direction, because the current is in the opposite direction to the motion of the electron. So this is now a very important thing that you are going to have to be aware of, because it's going to change Fleming's left-hand rule slightly. But now let's take this example, and I'm going to use this idea where I have this electron. Let me move it down slightly. And I'm going to put it into a uniform magnetic field that is going to move into the surface of the screen. Okay, so I have my electron here that's moving in this direction, and I have a uniform magnetic field, which we're going to note like this. So equally spaced apart, and remember this cross means that it's going into the screen, and we're going to then see what kind of forces are acting, or what direction is the force that acts on this electron, since if we know that the force acts because there is a charged particle there, then there must be a force acting on this. But we can no longer apply this this equation up here, because while we do have a magnetic flux density, we're not necessarily looking at a current anymore. This is a single electron. We can't say that's the charge per unit time, because that's just one charge, right? And we can't say we have a certain length of wire that's submerged, because this is a single electron. So we can't say this anymore. We have to kind of figure out what would this force be if we were to just break down the current into just a single electron. So we're going to do that here and say that force is equal to B times I times L, but we also know that I is equal to Q over T. Okay, so if I wanted just a single charge, I could simply just substitute in this as being BQL all over T. Okay, so I substitute in this I here, and I get that F is equal to B times Q times L all over T. And now I can notice that actually this L is not the length of the wire that's submerged, it's actually the distance that the electrons have traveled. Because if that's the distance that they've traveled in some amount of time, then L over T is just the velocity of that electron, because this is a distance divided by time. And hence I can say that F is actually equal to BQ times the velocity of the electron. And this is how forces behave in free space. So if I have just a single electron, I know the charge of this electron. Let's assume I know the magnitude of this B field. Only its velocity is going to change the amount of force that we have. And I could do the same thing here. I could apply this to a proton. I could apply it to a muon. I could apply it to an alpha particle. I can do anything, right? Now I have this equation. This is the second equation on your formula sheet that is going to explain how the force behaves on just a free charge that can roam around in space. Now we need to look back at this Fleming's left-hand rule and try and come up with a direction for the force to act in. Okay, so let's first say that we already know that the B field is going to go into the screen, and we know that the current is traveling in this direction. Okay, so this is the current, this is the B field. We can then, if you right now get your Fleming's left-hand rule, your index finger is your B field, because remember it's an FBI gun, and the index finger is your B, your second finger, so your middle finger, is your current, and so you need to have your magnetic field into the screen, and then rotate your hand until your current is following this direction, and you should find that the force is actually acting in this direction. Okay, so that means that as soon as the electron starts traveling in here, it's going to get pulled with a force downwards. So we can then assume that its path is then going to look something like this. But then we have to say, okay, what about when we get to this point? Because surely then I'm going to have a velocity that's going in this direction. Okay, my magnetic field is in the same direction, but now if I have a second case, so this is case 1, which I'm going to note here, then my second case, which is here, my B field is here, but my current is now at an angle, which means my force is now at an angle also. And you can probably tell from this point that now I'm going to start getting pulled towards the center. So as I was pulled down here, I'm now going to be pulled to the same direction. As I go round, I get pulled in, and this is a centripetal force. So moving charges have circular motion in a magnetic field. So now let's investigate this in a little bit more detail. If I were to set up some more examples, so let me just redraw out this electron example, and we know what the result is now. So if we had an electron that's traveling with a speed of v into this uniform B field, we know it's going to start rotating with a circular motion, and it's going to follow this kind of path, right, where it's going to travel in this direction. If I were to then start a proton traveling with the same velocity v into the same strength magnetic field, okay, so this is my B field, now the current does follow the same direction as the velocity, because I'm following the positive charge, and hence that means if my B field is going into the screen and my current is this direction, you can then test with your Fleming's left hand rule that the force should now act upwards, and again as it starts to pull around, it's going to start to curve, and you're going to get this curvature here, and you will end up with yet again a circular motion. So any charge traveling through a magnetic field, because it is charged, it will feel a force, and that force will happen to be a centripetal force because of this Fleming's left-hand rule. As your current changes direction, your force will also change direction, because they always have to be perpendicular to each other. Now from here, you can get some pretty cool things. So one of the reasons that we know the electron has a much smaller mass than the proton, originally we had no way of measuring the mass of an electron because it's tiny. It's almost impossible to actually get an accurate measurement for the electron without having a huge uncertainty. So what the experiment did was we put this kind of setup where we fired electrons in a magnetic field, and we measured the curvature of their path, and we did the same thing with protons, and we measured the curvature of their path. And actually what we find is if this BQV is a centripetal force, I can equate it to mv squared over r. I can then cancel out a v from both sides, and I have a q and an m here, so I can actually rearrange and say q over m is actually going to be equal to v over r times b times q, or just r times b, since q will stay there. And this gives me my charge per unit mass, and this is therefore a equation for the specific charge. And this means we've said initially the velocities are the same, and we know they're going into the same magnetic field, so it's only their radius that it depends on. And so if we have the same charge on both of them, since we just know one of them is positive and one of them is negative, whichever one has the smaller mass will end up with a smaller radius. Since I have a higher specific charge, I will have an inverse proportionality. So since electrons we can calculate have a higher specific charge, they will end up with a much smaller radius than a proton, which has a much larger mass, and so will end up with a larger radius. So smaller charges have a smaller radius, or even smaller masses have a smaller radius. And actually this again is kind of an inaccurate quote to say, I guess, since if the charge is then much bigger, I'm then going to vary my result. So to be more specific, I should say, let's just say what we said originally, which is that the specific charge, so I'm going to write it here, specific charge is inversely proportional to the radius. Okay, so if I have a very large circle, it must mean that I have a very small specific charge, or smaller than whatever I'm comparing it to. And this is how we are going to look at charges moving in free space. We're going to refer back to this idea when we look at nuclear physics as well, since this is again very closely attached to nuclear physics, being able to separate protons and electrons by putting them in the same magnetic field. They will then rotate in different directions. And so the important things to take from this video are that we can, well, probably the most important is we can still apply Fleming's left-hand rule, but we have to make sure the current is in the opposite direction to the electrons, in the same direction as the positive charges. And that we have to then readjust our equation F equals BIL to F equals BQV, so that we can actually apply it to just a single charge rather than a system of charges, which is effectively what a current is. And that all charges will have a circular motion in a magnetic field, and they will travel in opposite directions. Their radius can change depending on their specific charge. Thank you for watching.